In the separation process adsorption, you have one stationary phase and one mobile phase. The mobile phase can be a gas or a liquid, and the stationary phase is a solid with a surface that interacts with some of the molecules in the mobile phase. To illustrate the process, we here have a mobile phase containing two different components, red circles and blue blobs with a V-shaped dent in them. The surface of the stationary phase has triangular sides of the same size and shape as the V-shaped dent in the blue molecules. Thus, when the mobile phase comes in contact with the solid surface, the blue molecules stick to the surface while the red circular molecules do not. Consequently, if we let the mobile phase flow past the stationary phase, we can separate the blue molecules from the red, since the blue molecules on average will have a longer residence time in the system. We want the stationary phase to have a large surface area. Hence, the stationary phase is often porous particles. The porous material is often silica, zeolites, active carbon, a polymer, or a gel made of agarose or dextran. The size of the porous particles matters. With smaller particles, you get a larger inner area per cubic meter of material, since smaller particles can be stacked together more closely than larger particles. However, small particles give a higher pressure drop. If the pressure drop is too high, cracks can form in between the particles, so in the packing of the particles, decreasing the contact between the stationary and the mobile phase. With larger particles, you get less problems with pressure drop, but also smaller inner area per cubic meter. The exact mechanisms behind adsorption is not important in our course, but we often distinguish between ion exchange, where you have a charged surface with associated counterions that can be exchanged with some other ions. Adsorption, where a hydrophobic surface attracts hydrophobic organic substances. Adsorption, where a hydrophilic surface attracts polar molecules. And affinity chromatography, where you have a rather specialized bond structure between the surface and the molecule. The surface may, for example, have antibodies attached that attract very specific molecules, for example, proteins in the mobile phase. In this course, we will also talk about size exclusion chromatography, abbreviated SEC. SEC is, however, not an adsorption process. In size exclusion chromatography, the separation is based on molecular size only, not on any interaction with the surface. Let us look at ion exchange as an example. To deionize water, you can let the water flow through an anion exchanger and a cation exchanger. If you, for example, have water with dissolved calcium chloride, what happens in the anion exchanger is that hydroxide ions adsorbed to the positively charged surface of the stationary phase are exchanged with chloride ions, removing all chloride ions from the water. The water coming out from the anion exchanger is now free from chloride ions and can be fed into the cation exchanger. In the cation exchanger, hydrogen ions adsorbed to the negatively charged surface of the stationary phase are exchanged with the calcium ions, removing all calcium ions from the water. There is, however, a potential problem with this process. When you remove all chloride ions and let the calcium ions remain, you change the pH of the solution. Then when you remove all calcium ions, you change the pH again. This might cause problems, for example, if you're desalting a protein, since the protein might be stable only within a certain pH range.